Welcome back. This time we are going to look at yet another infinite series that can be used to find digits of pi. This one was discovered by Euler centuries ago. It is but one of his many contributions to a broad range of mathematics. He was quite a prolific fellow, and the advancement of mathematics owes much to this single person. Thank you, Euler. Here I have made a spreadsheet to implement what we saw on the previous page. The second column is 1 over n squared. The third column is the sum of every number in the second column up to that row. That is seen by the number boxed in blue. It is the sum of every number boxed in red. The value in the fourth column is the square root of 6 times that sum. Go ahead and make your own spreadsheet to confirm these numbers for yourself. We can see here in the last row that after 15 terms, we haven't even converged on 3.1. Not very good. Scrolling down to 1,000 terms, we have 3.14, 2 digits past the decimal. This doesn't appear to be converging very quickly at all. Plotting the terms, we can see that our method is converging from below. Unlike what we've seen elsewhere with oscillations alternating above and below pi, we cannot take the average to speed up convergence. Bummer. So what can we do? Nothing really. I'd recommend using a different method altogether. It turns out this is a poor approach if your aim is to find as many digits of pi as possible. However, the expression seen on the first screen has important implications to other areas of mathematics, such as number theory. We won't venture there, but I will show you how Euler derived this expression. Like just about anything in numerical methods, it starts with a series expansion. The first line is the Taylor polynomial for sine x. In the second line, we divide each term by x. So we converted an odd function into an even function. In the third line, we replace the argument by the square root of x. That simplifies to the expression seen in the last line. We now have a polynomial with a non-zero coefficient for each power of x. The roots of sine x are every integer multiple of pi, both positive and negative, including 0. We must square each of those to express the roots of the function sine of the square root of x over the square root of x. Let's look at some graphs to help this make more sense. Plotting y equals sine x, we see that the curve crosses the horizontal axis at integer values of pi, including 0. Next, plot y equals sine x divided by x. The curve looks a little different. In particular, the amplitude dampens out the further we get from the center. However, with the exception of x equals 0, this function has the same roots as sine x. It crosses the horizontal axis in the same locations. Now we plot y equals sine of the square root of x divided by the square root of x. No graph to the left of 0. Also, we see that the roots are different. The curve crosses the horizontal axis around x equals 10 and x equals 40. These correspond to pi squared and 4 times pi squared. So those are the roots. Now look at the last line. We saw it in the graphs, but remember from calculus that the limit of sine theta over theta as theta goes to 0 is equal to 1. That is why x equals 0 is not a root of sine x over x. Now let's dust off that stuff we learned in algebra class. Every polynomial can be expressed as the product of the roots minus the independent variable. r1 minus t times r2 minus t, and so on. We can divide both the left-hand side and the right-hand side by the scale factor a. Then in the third line, we factor out the roots. We can divide both sides by r1, r2, etc., which leaves us with the expression in the last line. Thus far, we've just rewritten the same expression in a different form by using some basic algebra. If we were to FOIL out all those individual terms, we would get an expression like that seen on the right-hand side in the first line. a0 plus a1t plus a2t squared, and so on. a0 is equal to 1. Try foiling this out to convince yourself that a1 is equal to the negative of 1 over r1 plus 1 over r2 plus the sum of the reciprocal of every other root r. a2 gets a bit more complicated, but we don't really care about that for our purposes here. What I've boxed in red is the important part for now. Remember this, we will use it again very soon. Now let's look at our function sine of the square root of t over the square root of t. This can be expressed as a general polynomial. In the second line, I've used the series expansion on the left-hand side and right-hand side. We've seen where both of these come from in previous slides. Equating values term by term, we see that a1 is equal to negative 1 over 3 factorial. This is equivalent to negative 1 over 6. Remember this. Okay, so now we put it all together. Negative 1 over r1 plus 1 over r2 plus 1 over r3 plus the sum of the reciprocal of every other root r is equal to negative 1 over 6. In the second line, we plug in the values for the roots, pi squared, 4 pi squared, 9 pi squared, and so on. Factor out a negative on both sides. Also factor 1 over pi squared out of the left-hand side. In the last line, we multiply both sides by pi squared. That leaves us with the expression seen at the very beginning. So now you have a better idea of where this came from. The sine function was quite important here. Once again, we see that trigonometry is intimately connected with pi. I realize there were a lot of details presented, so feel free to go back and watch this again if you need more time to absorb all the information. Also, don't hesitate to utilize the comment section below for a discussion of this topic. Next time we will look at a better method to find digits of pi. Thanks for watching. I hope to see you again.